Hello, this is Mrs. Taylor, and I'm going to introduce you to the fundamental theorem of calculus. This theorem was discovered by Newton and Leibniz around the same time, and basically what happened was both of these historic figures in math and science discovered a connection between integration and differentiation. And so, coincidentally, it happened at the same time that they made this discovery, and they both developed the fundamental theorem of calculus. And so, the theorem comes in two parts. Part one refers to the relationship between derivatives and integrals, and part two delves into how to actually evaluate an integral algebraically. And so in class, guess what? I've already taught it to you. So without even knowing that's what you were learning, that's what you learned. And so just a review of what we learned, now that we know that it's called the fundamental theorem of calculus. The fundamental theorem of calculus, part one, states that if a function f is continuous on the closed interval a to b, and capital F, there's a reason it's capital, it represents the antiderivative of f, your function, on the interval a to b, then the definite integral from a to b of f of x of dx equals the antiderivative evaluated at b minus the antiderivative evaluated at a. So this is what we did in class. We discussed how you could evaluate a definite integral by finding the antiderivative, that is the function whose derivative is this integrand. And then once you find it, you evaluate the antiderivative at your upper and lower limit of integration. So that's one part of the fundamental theorem of calculus. Just a note about notation, there is a difference between this lowercase f and the capital F. The lowercase f is your integrand, your function that you are integrating. The capital F represents the antiderivative. So if I took the derivative of this function, represented by the capital F, I would get the integrand represented by the lowercase f. So that's what that notation means. The second part states basically that the derivative and integral are inverses. So if f is continuous on an open interval I containing a, some constant, then for every x in the interval, the derivative of the definite integral from a to x of f of t dt with respect to x equals f of x. So it's almost as if this derivative and this integral cancel each other out, and you take your upper limit of integration, and instead of writing t, you write x. So one question is, why are they putting x here and t here? Well, the idea behind this is, this statement is basically saying that your integral is a function of its upper limit. And so we want to represent the fact that this relationship here is actual a function within a function. So f of t is a function itself, but when I integrate it, that integral makes it also a function of this of this higher limit of integration. The other way you can think of it is all my independent values from a to x. There's so many values between a to x. So if I put x here in the t's place, I would insinuate that this function could only take the value of what's here in my upper limit of integration, and that's not true at all. I've got to show that the function has an independent variable as well as this interval. So my interval could change, and the function's going to be changing, and so you have to use different variables to represent that there are two different factors that cause this scenario to change. So just a notation thing, a variable is a variable. It didn't have to be t's and x's. It could be any variables, but that's just what they chose. So, moving on to actual application of this information, which again we did in class. We actually in class focused on this part of the fundamental theorem of calculus, but just to give you an idea of how this part works into our section on the fundamental theorem of calculus, I want to give you an example of where this makes your life really easy. So let's look at a problem. So let's say I was asked to find the derivative of this integral. So they want me to take the derivative with respect to x of the integral from -2 to x of inverse tangent of t plus t squared over 4 plus 6 times e to the t dt. And so basically, as long as I remember this part of the fundamental theorem of calculus, this becomes really straightforward. Because the thing I have to remember is the derivative and the integral are inverses. So they cancel each other out. And so I actually don't have to do any kind of integrating or differentiating. All I have to do is realize that the derivative and integral are inverses. So what happens is I'm still left with this same expression. Except remember, your integral is a function of your upper limit of integration. So instead of writing t, I would simply plug in my upper limit of integration, which is x. So my answer would be inverse tangent of x plus x squared over 4 plus 6 times e to the x. Because the derivative and integral canceled each other out, and I just take my upper limit of integration and place it in for the independent variable. And so it's as simple as that. And so that's how the fundamental theorem of calculus fits into the big picture in our class. Like I said, the first part we reviewed in class already. The second part we will spend more time reviewing in class this week.